Hello. Okay, now let's talk about the octet rule. So, why do elements react to maintain this octet rule or maintain an octet of electrons? Well, um, as studies have suggested, a stable arrangement is when an atom is surrounded by 8 electrons at least. Okay? So this octet can be from an atom's own electrons and maybe some electrons they got from bonding with another element, and then they are shared. So when they are shared, that means they're available to both elements, and that forms an octet. Okay, and so atoms tend to react until there's an octet of lower energy than from whence it came. So chemistry is often governed by these energetic considerations and because of the octet rule. Okay, so when two atoms, so you see in this picture, two atoms, they're going to be attracted to each other because of the natural forces of positive and negative, but eventually there comes a point where they approach each other, and the opposing forces of attraction and repulsion are going to, make a concession and say, okay, this is the best possible arrangement that we can kind of agree to. And so eventually two atoms, they'll have a certain distance where they'll neither the attractive forces or repulsion forces are greater than the other, and they kind of form a neutral or stable state where the forces of attraction are equal to the forces of repulsion, and they are no longer fighting to repel or go against each other. Okay, so this optimal distance where these forces are the most stable is called the bond length, and the bond length is a force. It's not a physical thing. It's a force of attraction that's caused by the attraction of electrons on both atoms to the opposing nucleus of the other atom. And they're usually, the electrons are said to be within the bond, holding these atoms together. And it's between both atoms, because that's where the attractive force is the strongest between both atoms and the electron from the atoms. Okay. So I think this picture kind of details it very well and very effectively. And see here, the proton in on the center of two atoms, they don't change because they're localized in the nucleus. And then the electron, will be in the center because that's where it's most likely going to be, being both attracted to one nucleus of one atom and the other nucleus. Okay, so that's the octet rule. All right, so this diagram here is a measure of the potential energy versus the distance of the atoms from each other. Okay, so we see here when the atoms are too close, in this picture right here, atoms are too close. This is when the repulsive forces are greater. Okay, so right here, too much repulsion. So bond is too short, high energy, okay? And that's mostly caused because of repulsive forces. So repulsion from electron repulsion, and nucleus repulsion. So when those forces are too much, the energy will increase dramatically, okay? And see, as we move across, as we increase the distance, as the distance between two atoms get further apart, so what this R value is pretty much the distance between the two nuclei here. So if I draw two circles in the center here, that's what R is. So this is what R is, okay? So that's the distance between those two circles, okay? So if we imagine that distance is increasing, So at a point, it dips to where the energy is the lowest, and that's the point where a bond is formed. So the point at this, we call this a potential energy diagram. When the point, so when two charges are separated by distance, right, they'll have potential energy because they have potential energy to be attracted to each other, and so that is a potential energy, right? It's in this case, it's two distinct charges separated at a distance from each other. And if we kind of compare that to the mechanical version or the macroscopic version of potential energy, it kind of makes sense because an object is attracted to the Earth's gravitational field, and so when it gets too close, the potential energy dramatically decreases, and then once you increase your distance from the Earth, the potential energy increases again. So eventually, when we increase the R value, we dip, and we hit a low point, and that's the most stable point of energy for this system to form a bond. So that'll be the bond distance for, let's say, hydrogen. Now, as we increase the bond distance, you see the energy increases until it plateaus to like 0, where the potential energy is 0 because now the two atoms are, the electrons are nowhere near the other atom's attractive field or force. So we say the potential energy is 0 because there's no potential for a chemical bond to form. So as you increase the distance towards infinity, it'll approach towards 0. It'll never get close. It'll never get above 0 because they're not influencing each other. So there's no repulsive or attractive forces. So there's no potential energy. But but when we shrink the distance past the point where a bond can form, that's where we get a big increase in energy because now it's going to take more energy. It takes more energy to reach such a close state of these two atoms. So that's why the energy gets very increased like that. Okay, so that's how bond formation works. It has its roots in physics and also in this concept of what atoms like to do is achieve a state of lower energy. So that's why when we talked about light and photons, they go to a higher energy state when they get energy, and they naturally go back to a lower state of lesser energy because that's how elements and atoms behave. Okay, all right. So now let's talk about something called electronegativity. So electronegativity. So when atoms are involved in compounds like chemical bonds, they have a tendency to draw electrons towards itself because one atom is more electronegative than the other. Okay? So this concept is very important if students plan to go to organic chemistry or go into higher classes of chemistry. This concept will be particularly important. So here are the values of electronegativity. They were calculated based on experimental data that I will not go into. But these values will be useful for chemical bonding. Okay, so we can classify a compound as polar or non-polar, and we say, okay, is this polar or is it non-polar? Why or why not? And we can always come up with an answer based on an element's electronegativity. So the general trend is metals have low electronegativity values. So if electronegativity is below 1, it's not considered real electronegative. So to classify if a bond is polar, ionic, or nonpolar, usually we say we have differences in electronegativity values. Okay, so this means difference in electronegativity. So difference in electronegativity. All right. So the difference is less than 0.5. It's considered a non-polar covalent bond. Okay. So usually a type of bond like this is HH, CC, or CH. Okay? Something along those lines. Now, if it's between 0.6 to like 1.7, it's considered polar covalent. And if it's greater than 1.7 or towards like 2 to 4, it's considered ionic, an ionic bond. So for example, if we took sodium chloride, we see that chlorine is 2.87. So here's chlorine. Now here's sodium. Mine is 0.87. We get a value of 2.00. So that classifies as typically a classic ionic bond. Okay? So that's how we would classify these bonds. But we don't have to worry about these numbers too much because just by looking at a molecule, you should say, okay, well, they have two very different electronegativities, so they should be polar or should be ionic. Or they have two similar electronegativity values, so they should be similar. So this is kind of a trend you want to kind of devote to your heart because it'll be very important when discussing other topics of chemistry. So this is the one trend. This and atomic size is something I encourage my students to have a strong foundation in, especially when they move on to OChem. So it's important that if you do take OChem, you should do it right away. You shouldn't wait because if you wait too long, this information from Gen Chem might not be retained. So, and we don't want students to retake the class again. Okay, so that's something we want to avoid. Okay, so that's my recommendation. All right, so electronegativity. Tendency for an atom involved in a chemical bond to attract those electrons to itself because one element has a higher effective charge at the nucleus, so a higher atomic number in a row typically tells you, okay, this one is going to be more electronegative because it has more protons in the nucleus and it has less shielding, so no electrons and higher energy levels blocking the charge. So it makes it more effective at attracting electrons to itself. Okay, and that's why these values, they tend to decrease as you go down the periodic table. And that's because the charge from the nucleus is going to be blocked from electrons that are in higher energy levels. So it's like a defense force, right? It's harder for electrons to kind of get near the nucleus if there's already electrons kind of blocking access to the nucleus. So that's kind of an analogy I like to compare it to. Okay. All right. Okay, so now that we kind of got all those concepts down, we're going to go a step-by-step approach to writing Lewis structures. Okay. So, but one thing I want to mention before, if you look at this chart here, low electronegativity values, so metals tend to donate electrons, so they don't have high electronegativity values. And non-metals, they tend to gain electrons, right? So they're going to have high electronegativity values when they're in a chemical bond. So that's why these values tend to go this certain way in their trend. And that has to do with the fact metals don't like electrons, they want to lose them, and non-metals want to gain them. Okay. All right. So let's go to the step-by-step approach to writing Lewis structures. So first, we write the skeletal or skeleton structure of the molecule. So if you took chemistry in the past, this means you draw the arrangement of atoms on your piece of paper. And in general, the atom that appears in the center of the molecular formula is usually the central atom. And it's usually the atom with the smallest electronegativity. But that's not always the case. So there may be some exceptions. Okay? So first we determine the number of valence electrons of the molecule. So I'll go over how to calculate that in our example. And then the general rule here is we use 2 valence electrons to form a bond, okay, in the skeleton structure. So, okay, let's distribute the valence electrons in bonds first, and then we put the other, like, to account for the rest of the electrons. So this is where we get into like electron accounting here. We need to put them somewhere else in the molecule, and usually we put them around atoms that are bonded to the central atom as lone pair of electrons, and I'll go into what that means too. All right, and then lastly so that's what I meant by the lone pairs. We try to place 8 electrons in the valence shells of the atoms by distributing the remaining electrons as non-bonding electrons. So that's what I mean by lone pair of electrons. They're non-bonding, so they're not involved in bonding, but they're there to maintain the octet for all atoms involved. Okay. So, for example, let's draw the Lewis structure for phosphorus trichloride. So here we need to be able to translate from name into chemical formula. This is where it gets really important. All right. So phosphorus trichloride is PCl3. Okay. So looking back at our periodic table, phosphorus has 5 valence electrons. So we're going to say it's group 5. Group 5A. So 5 electrons in its valence shell. And chlorine in our case is group 7A. So 7 electrons in its valence shell, but we have 3 chlorine atoms in our formula, so we have to multiply it by the 3 here. So I'm going to underline it to indicate that that's where the 3 came from. So this would give us a grand total of 5 plus 7 times 3 equals 26 electrons. Okay. So now we have a total of 26 electrons to distribute in our structure. So let's first draw the skeleton of our molecule. So in this case, the first element is pretty much the central. Well, I wouldn't say all the time, but in this case, it will be. So phosphorus in the center. Then we're going to, position chlorine around it, kind of equally here, equally spaced. Okay, so now the first thing we do is we take some electrons and distribute it as bonds. So each time we form a bond, that's going to be 2 electrons. So 1, 2, 3. So we have 6 electrons as bonds. Okay, so 6 electrons as bonds. So now we have 20 electrons left over. So now the only thing we can do is, we'll go into when you need to add more bonds to a molecule, but in this case, we shouldn't, just because halogens, they don't usually like to form more than 1 bond, so we're not going to do that in this case. So now we put the electrons back as lone pairs. So now phosphorus doesn't have an octet yet. So let's put a lone pair here. So that's 2. And then now the chlorines don't have an octet. So let's put 6 electrons around each chlorine atom to make sure they each have an octet. So 1, 2, 3, 4, 5, 6. So that's 8 electrons I've added. 9, 10, 11, 12, 13, 14, so 14, 15, 16, 17, 18, 19, 20. So now I have a total of 26 electrons in my molecule, in my Lewis structure. So this looks good. So this is the structure of phosphorus trichloride. So that's how you would draw phosphorus. And the key to getting good at this is just to do practice problems and do so many practice problems that you see the exceptions, you know what to do. If you see a formula you haven't seen before, as long as you know the skills of how to write them and draw them, should be able to solve each one as they come. Okay? So this will be very important in other forms of chemistry because you have to draw a lot. So it's important that we understand how this skill is developed. Okay? All right. So let's stop this video here, and we'll continue with the next example in the next video. So I'll see everyone then. All right. Bye-bye.